Welcome to the second video of my Code It Yourself Synthesizer series. Today we're going to be looking at envelopes and oscillators. This is due to some feedback from the previous video. I'm going to keep it a bit shorter and a bit snappier. Hey, I'm still learning as I'm going along. And today I particularly want to cover the very basics of what we did last time, how the code is actually used as a synthesizer. In the last video we specifically talked about waveforms being the fundamentals of sound synthesis. But we didn't really use any of the synthesizer lingo, so I'm going to start introducing that today. And we'll be looking at some other waveforms, and we'll be looking at how we can shape the waveforms to sound like a more realistic instrument. In the previous video, we really just played about with sine waves, and we used a trick to turn those sine waves into square waves, and we listened to them. But there's other types of waves that we can play with. Now, in sound synthesis, these waves are called oscillators. I think it's time to take the original program and make some of it more convenient to use. It's going to get a little bit more complicated from now on. Now, some of the feedback I got from the first video is that the code wasn't always visible, so I'm going to experiment with dynamically zooming the code so we can focus on the parts of the program I'm talking about. Let's start by making some optimizations to our little program from the first video. One of the things we're going to see a lot of is turning hertz into angular velocity, so I'm going to wrap that up in a small function. So I've created a little function here, and it's going to be simply frequency in hertz times 2.0 times pi. Now pi is a constant defined in the OLC noisemaker header. And we'll just quickly test that, so we can get rid of the 2 times pi and wrap up our frequency in our function, W. We'll just compile that and click play. Yeah, sine wave with the clicks, but we also saw it in the first video. It would be handy to use different oscillators without having to rewrite the mathematics each time. So let's create a function called osc, which represents an oscillator. So our oscillator function will take a frequency input. It needs to take the current time, so we know whereabouts in our oscillation cycle we are. And we're going to have several different types of oscillators, so we need a way for the user to choose that. And let's put in a quick switch statement here. So depending on the type of oscillator, we can now choose a different function, and if there's an invalid type, we're just going to return 0, because it's probably the safest thing to return 0, i.e. there's no sound output. So it won't damage your speakers if it goes wrong. I should take this moment to actually say, be careful using this stuff. If you have really large amplitudes and very low frequencies, you could easily damage your speakers or headphones. I'm not going to be liable for that, so use with caution. Let's take a case of 0 for being our standard sine wave. So we want to just return the sine of frequency in hertz times d time. Simple enough. We also know how to do a square wave. If you remember, a square wave was just thresholding the sine wave around its middle. So we can do the same as before. Hertz times d time. What we want to test now is that greater than 0. And if it is greater than 0, we want to output a full amplitude of 1. And if it is less than 0, we want to output -1. I really do like the inline if then else syntax. What other type of waves could we include? Along with the sine wave and the square wave, we may also have the triangle wave, which looks like this. And the triangle wave is described as being the arcsine of the sine of our standard sine wave. It's scaled here at the front with 2 times the amplitude over pi. But it follows all of the same rules as we change the frequency, and we can change the amplitude. So let's add the triangle wave to our oscillator function. Triangle wave, and so this is the same as our sine wave again, but this time we take the arc sine of the result. And we do a little bit of scaling, capital Pi, and there we go. Let's take a moment to test these functions and listen to the differences. So in our make noise function, we now want to call our osc function. So instead of calling the sine function directly, we call oscillate. And we know that now our frequency output is in hertz. We need to pass along the time. And our first one shall be sine waves. Let's have a listen. So, nice, very mellow. Let's change it to a square wave. Much sharper that time and louder. Now let's change it to our triangle wave. Not surprisingly, it sounds a bit like a square wave and a sine wave mixed together. There are two other types of waveform. The next one is the saw wave. Now, there's two ways to generate a saw wave. There's the mathematically great way to do it, and there's the computer great way to do it. We'll look at both. The sawtooth wave is called such because it looks like the edge of a saw. Here we can see the wave increasing and a rapid fall. So we've got a slope and a fall. To generate a sawtooth wave mathematically, we sum up all of the multiples of a particular frequency of a sine wave. So if we take, for example, 110 Hz, which is one of our A's from the last video, we would add to that 110, we'd add a frequency of 220, we'd add 330, we'd add 440, each time scaling it a little bit, but summing up all of these sine waves. And this really cleverly gives us a sawtooth wave. And so we can see here in the function we're summing up all of the waves up to a number of sine waves here. This is the count of the sine waves. And if we have one sine wave, we add it. As we add it, we can see that it becomes more linear and more linear. And the idea is this goes off to infinity and you get a perfect sawtooth. However, adding up sine waves in this manner is grossly inefficient for a computer. So we can also apply a hack to this using the mod function, using computer rounding, integer mathematics, to simulate the addition of all of these sine waves to give us a perfect piecewise linear approximation. So here, if I enable this, we can see the computer function here using the mod function gives us perfect linear black lines here. So straight up, straight down, straight up, straight down. I think there'll be some difference acoustically between these two waveforms, so I'm going to include them both in the oscillator function. Here is the code for two implementations of the sawtooth wave. This first instance 3 here is for the analog version. I've called it analog. It might feel a bit warmer, and it's definitely computationally slower calculating all of these sine functions. If we just quickly go back to our Desmos here, why have I said it's warmer? Well, because if I change the number of sine waves included in the summation, we can see that we get an interesting characteristic. It's not just straight lines. And I think that these will sound acoustically interesting, and so I'm going to call that warmth. As opposed to the alternative, which we'll just look at the code, is using the mod function. In this case I'm using fmod because I'm working with doubles. And I'm using the time period, so as time progresses along the x-axis we mod it with our frequency or period, which is 1 over frequency. So that will give us our straight line slope, and we're offsetting and scaling in both instances to make sure that we lie between -1 and +1. So I'm curious to see what these sound like. So I'm going to make sure that we're using number 3 here, and so this is with 10 additions of sine. It already sounds much better than the standard sine wave and far less harsh than the square wave. Let's try it now with, say, 50 additions. Definitely getting that retro feel now. Let's go up to 100. Well, I think that sounds ace. Now let's try our approximation. So this time, instead of calculating sine 100 times and doing divisions, we're just going to calculate the mod function once. So we need to change it here in our make noise function to index 4. Now, I think that that sounds very similar, but not quite the same. I might be fortunate enough to be listening to this through my headphones. You'll have to try the code yourself and see if you can discern a difference. I think there definitely is one. I think that this method sounds far more clinical. And I don't want to start some big audiophile fanboy argument about whether vinyl sounds better than MP3. But there's certainly something to be said for the additional detail in the signal of the addition of sine waves as opposed to the coarse mod function. There is one final type of oscillator source which we've not included, and that is the introduction of pseudo-random noise. I can't graph this in Desmos, so I'll just assume that you know what a random number looks like, and in this case I am using the C++ rand function. Please don't write in, I know it's not the best random number generator in the world, but it's good enough for this purpose. So we need to do lots of casting here. Yes, yes, I know, not good. So I'm taking the rand and, oh, brackets in the wrong place again here, and dividing it by rand max, and I want to take the whole thing, offset it, and we're going to scale it. So this should give us a random number between -1 and +1. And it doesn't matter what the frequency is, of course, because we've not included it in our calculations. However, just to prepare you, because our frequency output is shut off down here, if we're not pressing a key in the code, we just simply set our frequency to 0, that's not going to silence this oscillator. So as soon as I start this program, we're going to get a random noise sound. And here we go, are you ready? Turn down your speakers. And what's this for? Well, some percussion, maybe later on. And what would be nice to try in a future video is blending together different oscillator sources to try and come up with more interesting textured sounds. For the time being, I'm going to set this back to our analog sawtooth wave. I like it. At number 3. Now, a musical instrument isn't just simply a on-off sound. The sound's volume will change during the period of the note, its frequency might change. So we need to introduce a property called envelopes or envelopes, depending on where you're from. Let's consider a church organ key being pressed. We'll first of all draw ourselves an axis. So here we've got some time, and here we've got amplitude. So we're going to change the volume of the signal as time passes. And there's two interesting points in time for a key press. First is, when is the key pressed, and when does the player release it? So we'll have that as our press, release. So what happens when let's say the church organ key is pressed? Well, there's pressure in the pipes, and that pressure is built up and released, so we get a sudden surge of sound. But this takes some time, and we call this the attack time. Once that pressure is released, it actually just releases a little bit here. This is our decay time, because it wants to settle at a particular volume. The pressure has suddenly been released, and now we've reached a state of equilibrium. So this becomes our decay time. And the church organ will continue now blowing air through the pipes until the player releases the key and the valve switches off. And this is called our release time. So these are 3 important times. And in between, this time can be however long the player has got the key pressed on the keyboard, but it sits at a particular level, and this is called the sustain level, or sustain amplitude in this case. So that gives us 4 components to this envelope, which is the attack time, the decay time, the sustain level or amplitude, and the release time, which is the time taken for all of the sound to stop. Any real instrument cannot do things instantly. It has to obey the laws of physics, so things take time to happen. Only virtual instruments can break these rules, and that's why you can get some pretty funky sounding synthesis sounds. Now let's consider a slightly different instrument. Let's consider a guitar string being plucked, but no note being held, just plucked. In this case we have an attack time, as before, but we probably don't have a decay time, and there is no sustain. The note has been plucked. There is no more energy being fed into the system to keep the sound alive. So we just have a release. A release time. So for plucked instruments, the envelope can be much simpler. It's now time to start writing some real code. As much as possible I've tried to keep things very simple, but unfortunately we're going to have to start introducing more complex code, which will take some study. I don't think I can just get the point across straight away. You'll have to look at some source code. But we're going to create a structure to represent our envelope. And in the synthesis world, these are ADSR for attack, decay, sustain and release, as we've just seen scribbled out. So what properties do we need to store as part of our envelope? Well, we're going to keep everything as double again. We know that we've got the attack time is required, and we've got a decay time, and we've got a release time, and we know that we've got an amplitude for our sustain. The initial attack might go to quite a different amplitude than the note will rest at. In fact, let's capture that amplitude as well. And we'll call that the start amplitude. Even though the duration of a note is known by when the player presses the key and releases it, the duration of the envelope might be longer because it takes time to release the key. So we need to know when has the user pressed and released the key, and the envelope will then tell us what the amplitude should be at any point in time. So let's capture 2 more variables for D, trigger on time, and double D trigger off time. So this is when the key is pressed and when the key is released. Let's default some values. And everything is in standard units, so if we want our attack time, let's say we want it to be 10 milliseconds. There we go. The envelope can be indexed at any point in time by our makeNoise function. So we need to return the amplitude of this envelope for a given time. To make this easier to work with, let's add some methods for note on and note off. So when a note is pressed, we'll need to call the note on function. And when a note is released, we'll call the note off function. and these simply capture the time, trigger on time, sorry, and off time. Because the release phase happens once the key has been released, we'll probably need to store a state that says whether the key is up or down for this envelope. So let's throw in here a quick bool and initialize it. Let's add the guts of the ADSR envelope structure then. Well, D time here is real time in the song, the piece of music, whatever the wall time is. So we need to turn that into an index into the lifetime of this envelope. That's simple enough actually. So we call lifetime of the envelope is simply the current time being passed to this function, taking trigger time, taking the start point. So this gives us the time after the note was pressed. So as soon as the note is pressed, lifetime is 0 and increases from 0. We know that there's two distinct phases here, either the key is held down or it's not. So if the note is on, we want to do something, else we want to do something else. So in fact, when the key is down, we want to handle the A, D and S parts of the envelope, and when it's released, we want to handle the R parts of the envelope. So let's start with the attack phase. So if our lifetime is less than the attack time, we know we're in this attack phase, less than or equals to down. And so our amplitude, what I'm going to do here is normalise the attack time by simply time divided by D attack time times D starting amplitude. And we're going to see notation like this a fair bit. So what I'm doing here is actually creating a value between 0 and 1. So if the lifetime is less than the attack time, let's say the attack time is 5 seconds and our lifetime is 0, here we've got 0 divided by 5. However, after 5 seconds, or let's say 4 seconds, we're approaching 5 seconds, our lifetime here is 4 divided by 5, and eventually we approach a 1 here. So we're going from no amplitude to 100% start amplitude. Now, the decay phase only happens once our lifetime is greater than our attack time, but less than the total of the attack time and the decay time added together. Time is greater than the attack time, and decay time is less than Let me just help visualise that. We're breaking it up now, so we've done our attack phase, which is there, and now we've got our attack and decay phase. So you can see that's the summation of both this time and that time. So in a similar way to above here, we're trying to create an index between 0 and 1 of how far into the decay time period we are. And it's quite a long line, but we're taking our index into the decay time, and this time our gradient is defined by the sustain amplitude minus the start amplitude. Now the sustain amplitude will typically be lower than the start amplitude. It doesn't always have to be, but it can be. So let's think about the sustain phase. So we know that the sustain phase exists once we've done both the attack phase and the decay phase added together. So if the lifetime is greater than attack time plus the decay time. The nice thing about the sustain phase is it's a constant amplitude, there is no change. And that's been described in our structure. So any time after the attack and the decay phase is finished, we exist, and the key is held down, sorry, we exist in our sustain phase. So all we can do is output a solitary volume. Now, in our release phase, we want to do a similar thing to up here. We're getting the lifetime, but instead of the trigger on time being our starting point, we now care about our trigger off time. So again, it's the amplitude being outputted, and instead of the trigger on time, we want the trigger off time. And as before, that is normalized to our release time. So we're getting a 0 to 1 value of the release phase. We're going to put in a little check here called an epsilon value check. And this is to stop signals coming out of the envelope that we don't really care about. They're so low that we can't hear them anyway, and they just might cause problems not having things set to 0 if they're below a certain value. My apologies for that being a big chunk of code, but I think it was a useful exercise. We now know how we can use time to index into an envelope to control the amplitude of our notes. Let's put this into practice and have some fun. So the first thing we're going to need is actually the envelope. Spell it correctly. Envelope. Now, because we have a constructor in this struct, the values are defined when the variable is created. To use the envelope, remember that the envelope controls the amplitude. We want to modify now our output. So whereas before we were hard coding numbers here, we're now using the envelope itself to give us the amplitude at a point of time. We need to link the envelope with when the note is pressed and released. So we can do this with our note on methods, and we also need to provide this with the current time of the system. Now, the OLC Noisemaker class comes with a function that will give you the current time. So we're going to use that. Sound.getTime, and we need the equivalent note off as well. Now, here's an important thing. Our sound is now controlled by an envelope. So having a frequency output here means that whenever the key is released, the frequency will be set to 0. So none of our release phase will work because there'll be no frequencies to listen to, regardless of the amplitude. So we need to remove this line. And that should be it. So let's see if we can get any sound. Well, I think that sounds quite cool, but you can barely tell that there's anything happening at all. Let's slow down our attack phase and our release phase and see what happens. So to do this, we can change the values here in our constructor. So instead of 10 milliseconds for the attack, let's set that to 100 milliseconds, and instead of 20 milliseconds for the release, we'll set that to 200 milliseconds. And we can press a note. So I press the key and release it. Press, release. It's no longer an on-off key, it fades in and it fades out. Very nice. And there you have it, we've implemented an envelope. Now, as a little bit of bonus content, I want us to play with the oscillators we created at the start of the video. Here I've adjusted the make noise function to use the envelope as it was before, no changes. But what I'm doing this time is using the envelope to modulate the addition of two different frequencies. So if you remember, 3 was our sawtooth generator and 1 was our sine wave generator. Now for the frequency, I'm halving it for the sawtooth. and I'm keeping the sine wave as it stands. Let's have a listen. And though we've got a very textured instrument, this is definitely starting to sound like a usable synthesizer. Thanks for watching this video. Today we've covered envelopes and oscillators, and in the next video I'm hoping to cover filters. I've tried to take on some advice and keep this one a bit more concise, so I'm sorry if it's sounded a bit rushed. All of the source code is available on the onelonecoder.com blog and from the links below. If you've enjoyed this video, please give me a thumbs up. It all helps.